Welcome everyone to the second day of the workshop. So this morning we'll have again 2 2-hour talks. The first talk is given by Professor Xiantao from Penn State University, who has done amazing works in quantum algorithms for Lindblad equations, and I think he will tell us about how to simulate these Lindblad equations.
Thank you, organizers, for inviting me here and for the opportunity to talk here, and more importantly, to interact with a lot of the people at the conference. My talk is going to be about simulation algorithms, and I'm going to focus on the Markovian regime, namely the Lindblad equation. And in addition to that, I'll try to keep my talk at a sort of a high level so that I can sort of tell you about some of the basic ideas in the constructions of these quantum algorithms, instead of diving into too much technical details. And my hope is that this can jumpstart some further discussions along this line. Now, many of my collaborators are actually here. So if some questions come up, and they can help me give a better answer. Now, before I tell you about quantum algorithms, I'm going to say a few words about classical algorithms, because some of these ideas are actually motivations for the quantum algorithms. So including, for example, a stochastic trajectory-based algorithm or the structure preserving method. Now, in the last few years, there have been quite a few quantum algorithms that are designed for simulating Lindblad equations. So I'm going to focus the discussions on 2 of these works. And this is where one can prove some complexity estimate. And the complexity seems to be nearly optimal. Now, I'm not going to talk about thermal state preparation. One is that there are already many experts here, and 2 is that I don't know much about it. Instead of that, I'll talk about another application where Lindblad simulation can be useful. And this came up in quantum optimal control problem. And this is one place where you have to repeatedly simulate the Lindblad equation to solve the optimization problem. And therefore, an efficient Lindblad simulation algorithm would find its place in this particular problem. Right? So that's kind of the overall structure of my talk. Now, when it comes to the Lindblad equation, my view is actually the same as Sandy's perspective. So we can think of the Lindblad equation as coming from sort of 2 different paths. So the first path is to consider system bath coupling, where you make some standard assumptions, and what this induces is a CPTP map. And then if you make further assumptions on the coupling strength and the timescale separation, you can derive the Lindblad equation, right? And so there are some mathematical papers, but there are also some physics papers. We particularly like this book, which kind of explained this passage from the system bath model to the Lindblad equation. And there are also interesting examples that are given in the book. Now, the other path is purely mathematical. So your starting point is a semi-group representation of the dynamic map. And then you're starting with this together with the CPTP property. These 2 papers in the 76 also derived this general form of the Lindblad equation. Right? So knowing where this is coming from actually is helpful in terms of thinking about designing algorithms. And also, this also provides an opportunity to think about going beyond Lindblad, right? Of course, I'm not going to talk about that today, but it's definitely an interesting question to move to. Now, when it comes to classical algorithms, the textbook example is this Monte Carlo trajectory idea. So you start with the Lindblad equation, and you separate out the commutator and the anti-commutator term, all right? And so what this gives you is this system Hamiltonian and this sort of non-Hermitian part, right? And you can first try to drive the system with this non-Hermitian dynamics right here. And of course, this process is not norm preserving. You're losing some probability, right? And so then you decide either to stay proportional, to be proportional to this state, or jump to some other state, right? And so you have to figure out this probability that the system is going to collapse to this particular state. This Lj is one of the jump operators in the Lindblad equation. Now, in the implementation, the step size is actually a random variable. You actually have to determine that random variable so that it can coincide with a random number that you draw. Okay. Now, in the book, there's a nice interpretation of this in terms of a stochastic differential equation or stochastic Schrodinger equation. Now, this is a stochastic Schrodinger equation. If you so if you look at this coherent part here, this is the original Schrodinger equation for closed quantum systems, right? Now, the rest of the terms here comes from the interaction with the environment. And what's special about this SDE is that the second moment actually follows exactly the Lindblad equation. So I'm going to talk more about that in a few minutes. Now, this algorithm seems a little complicated, but in the sort of SDE literature, there are other approaches for approximating the solution of this SDE, which will produce an approximation of the Lindblad dynamics. Just classical vectors, just matrix vector multiplication, right? And then you do have to draw these, for example, these Poisson random variables. Yeah. But this is a bit more complicated because you can see that some of the terms are actually nonlinear, right? A much simpler SDE representation is actually an SDE that's driven by Brownian noise. Okay? And so this is another sort of version of the stochastic Schrodinger equation. Again, here you have sort of the dissipative part, and then this is the jump part, right? Now, you might ask me, who gave you the freedom to pick which SDE to simulate, right? But it turns out that both of these two SDEs reproduces the Lindblad dynamics exactly. So we get to pick the simpler one, and this looks simpler, right? So once you have this SDE, you can just go to the SDE literature and draw some classical solvers, and there are many of them. And so the typically one start with the Euler-Maruyama method. All right.
Why do most of the textbook come from derive the previous one first?
I think it has more sort of connection with the physical picture, right?
And also the numerical performance of the first one seems to be a little bit.
I don't know, actually. So I think in the end, to evaluate it, you have to look at the variance, right, and see which one has.
I mean, this one seems like the variance is large.
I actually don't know. I don't have first-hand experience. That's a good observation. Yeah. So if you want to determine the variance, you can actually write down an equation that governs exactly the variance. So if you want to compare them, it's actually not very difficult. And so again, these SDs exactly reproduces the Lindblad dynamics. Now, the nice thing about this typically is that it preserves the CP property, right? Because you're taking these ensembles of pure states and you're taking the average, right? And then by plugging in these standard solvers, you usually get the CP property. And you're only working with a vector here instead of a matrix, right? But so it looks like you need less memory, but you do require a lot of samples, right? So that's where the main computational overhead comes from. Now, the other approach would be just to look at Lindblad equation as a set of ODEs, right? Let's say that the problem is finite dimensional, then it's just a set of ODEs. So what's wrong with the standard Runge-Kutta methods? Let's take an example. So let's strip away. So some of the terms, let's say the coherent term, and let's only keep one of the jump operators, okay, as an example. And if you apply the Euler's method, right, usually this is the first thing that we teach our students, what you can show is that this approximation right here does not preserve the CP property. And you can check that there's a matrix over there that's not semi-positive definite. And so if the CP property is something that you care about, then you have to think about something else, all right? Otherwise, if you don't care about the CP property, you can just go with high order Wang-Lakuta. And for classical algorithms, there's nothing wrong with that. Okay. All right, so how do we come up with an approximation that looks like this, but still maintains CP? Okay. Right. Well, so right, for this one, you don't have to. So in the previous one, I think that's where the nonlinear terms are coming from.
Well, if you don't do it here, you won't preserve norm.
It preserves the norm on average after you take the expectation.
Sure.
Yeah. So it's not going to be norm preserving pathwise. Yeah. Right. And so this question was solved by Cao and Lu, and this is Jianfeng's paper. And the idea is based on a Duhamel's principle. And the first step is to separate the Lindblad operator into two groups. And we kind of have done that in the first few slides. You kind of group together the commutator and the anti-commutator term, right? And so this leads to in non-Hermitian dynamics. And what you have left are these remaining terms, which are in the Kraus form. Okay. And then you apply the Duhamel's principle. So this is not about operator splitting, although we are separating the operator into two pieces, right? You actually use the variation of constant formula and write down an exact equation, although it's not a differential equation, it's an integral equation for the density operator. And at some point, I was curious about where this formula, who came up with this formula in this particular context. And the farthest that I can trace back to is this paper, but I do suspect that people knew about this before that. Okay. All right. Now, this formula itself doesn't solve the problem because rho is still involved in here, but you can play this game over and over again. Namely, you take this rho and plug it in here. That produces two more terms. And in the end, you can write down an infinite series of expansion for the dynamics here that represents the dynamic map exactly, right? Now, and then at some point you have to make a truncation. For example, if you want to truncate the infinite series here, you can plug in the initial density operator, and then the right-hand side gives you a closed form formula that you can implement. Now, what is cool about this formula is that if you think about what this operator Lj does, well, it puts rho between Lj and Lj conjugate or dagger, right? And so it gives you a Kraus form. And this form here, because of this particular form here, when it's applied to a density operator, also gives you something that's like a rho sandwich between one operator and its adjoint. Okay. And therefore, in the end, you're getting a Kraus form approximation, which preserves the CP property, okay? Because composition of CP maps are also CP. Okay. Now, if you want to get to arbitrary order of accuracy, you can keep on doing this. I'm going to show you that formula in a few slides. So to actually implement this without destroying the Kraus form, you need to approximate this matrix exponential. For example, you can use Taylor approximations, and you need to approximate this integral. And for example, you can use numerical quadrature. And so, so here I'm talking about classical algorithms, so it's just a matrix. Right, I guess. Yeah. Yeah, I don't know if people do that in practice. So now I'm moving to quantum algorithms, and I'm not the first one to work on quantum algorithms for simulating a Lindblad equation.
The Taylor extension for the non-trivial part.
Or classically, that's Jeffrey's work. I forgot what he did.
They want the question to be positive.
There's literally.
There are probably other ways to do it as well.
Interesting.
I would imagine maybe some
Not
sort
like
of
a parallel.
trade-off subspace would work too. So I think probably the first paper where the algorithms for Lindblad equation is designed is this 2011 paper. And the complexity of this in terms of the time duration and the precision parameter is like order t squared over epsilon. And later on, Kraus and Li, this is not me, it's Tongyang Li, in 2017, they proposed two quantum algorithms. And the overall complexity has a better scaling, right? And the reason that you get this kind of scaling is because, for example, one of the algorithms is similar to the Trotter, the second order Trotter, okay? And the reason that you cannot go beyond that in this particular setting is because the Lindblad equation is not time reversible. So you cannot have negative coefficients, okay? So that's where the order got stuck here. And an important progress along this line is this paper by Cleve and Wang, this is Chunhao's work. And also in 2017, but this came out after this paper. And they came up with an algorithm that scales with t only linearly, with epsilon only polylog form. Okay. So the idea is to first start with an approximation in the Kraus form. Okay. And this Kraus form has these Kraus operators that look like this. And this looks similar to the Euler's method that I mentioned before, but it has one extra term, which makes it CP. Okay. And then I think Trinhao also mentioned something along this line yesterday, that this method is only first order. So to ensure that the accuracy is within epsilon, you have to use fairly small step sizes, meaning that you have to use many, many steps to get to certain point. And in the end, if you repeatedly apply this Kraus operator, you end up with many, many terms. So you need a compression scheme to single out the ones that are important. The technical, the other technique used in their paper is the block encoding and the generalization of the LCU, right? And this is previous amplitude amplification for isometries. So these jump operators are going to be block encoded. Yeah, go ahead.
For the block encoding, like whenever they use the block encoding, does it come to be one or
Does it come out to be what?
so I'm just asking. So this algorithm uses block encoding, right?
Right.
So they will use this as oracle.
That's right. That's right.
So whenever they query oracle, they call the counter cost to be one or to be something ON.
Wait. In this paper, we didn't use block encoding. We used the sparse access oracle, and we counted how many oracles we use.
Sorry,
But sparse access oracle can be turned into block encoding with.
I think I'm asking.
Yeah.
So I'm just curious, like, so when you, I mean, okay, you query a sparse oracle. So when you query oracle, do you count the cost as one?
Mm-hmm.
Okay.
Right. And so, he was 3 years later, Chunhao came to Penn State, lucky for me, all right? So we started thinking about whether we can simplify that algorithm to get rid of the compression scheme, right? And
can you say a little bit about what goes into that compression scheme?
I think it's like a lot of Hamming weight, and then you pick the ones that are significant. I don't exactly know how this works on the circuit, but maybe Chunhao can comment on that.
So we have a lot of pieces. So the idea is that when you have a lot of pieces of the controlling register, then you observe that most of the amplitudes are concentrated to identity. Sorry, concentrated to 0, 0, where 0, 0 is controlling the identity, which is doing nothing. So we just bound the Hamming weight of this controlling register. And that's the compression scheme.
And that compression is the same as the one used in Chen Gideon.
Not the same. So in the original compression scheme, we had a bug, then Andreas pointed out, then we fixed it, but not posted yet.
But after the correction becomes the same, or?
No, not the same.
Still not the
Two
same.
different compression scheme.
Okay, yeah, thank you.
So what made this simplification work is this Duhamel's expansion. So I told you a few minutes ago that we can expand this density operator using the Duhamel's principle into many, many terms. And you're going to see the nested integrals, right? But overall, this gives you a cross form of the approximation. Now, we also mentioned that we gotta approximate the integrals, right? And so, of course, given the number of quadrature points, the best quadrature formula there is the Gaussian quadrature, right? And so, what this provides you is that for each layer of the integrals, you don't need that many quadrature points. So that's the first thing. So the second benefit is that in the end, like in the previous slide, you're seeing sort of a linear combination of the Kraus operators, right? To actually implement that, we need to figure out the coefficients, the sum of the coefficients. And this is where we took advantage of these special properties of the Gaussian quadrature, where there were some really nice identities for the quadrature weights and the quadrature points, okay? And you can easily estimate the sum of these coefficients. I think that's the next line, right? And because of the maximal order of accuracy and this nice formula right here, in the end, the truncation of this infinite series doesn't have to be very far. So this capital K only scales like log of 1 over epsilon. And the number of quadrature points that you need is also has the same scaling. Okay. So this gives you a very compact sort of approximation scheme without having to deal with many of the terms. At this point, no, but later I'll talk about the time-dependent Lindbladings. So it's going to come up in the Lindblad control problem. So this is sort of the overall complexity. Now, right. It is 1. Oh, sorry. So this is basically come from the property that it could be, there could be a typo, but this comes from the property that a Gaussian quadrature is exact for high order polynomials up to like 2 times k or something, or 2 times q.
How this fits into the quantum algorithm? So are you imagining an oracle that would give you that whole sum?
So those are built from the individual ones. So I think in our paper we actually use. So actually, you block encode the jump operators first. So that's like the input model. answer the right question.
So all you need to do is buffer code that.
That's right. That's right.
And then get its evaluation at the different time points.
So the Lindblad operator right here is time independent, right?
But in the next slide, when you have the sum, don't you need the function, like the exponential evaluated at?
Oh, you do it step by step, and each step you follow, follow this by the previous amplitude amplification.
I see. So
You boost the probability to 1.
And then is this sum done coherently, or are you just extracting the sum ends from the one algorithm and then doing the sum?
Coherently, what does it mean?
Linear combination of unit.
I see. You just treat this as big LC.
Last question, yeah, so is in the previous slide, so how does the time complexity depends on the system size?
So logarithmic, I think, right? Or the input model here is like the log encoding, but I would imagine that's a logarithmic. Logarithmic. So, oh yeah, thanks.
You need to implement that e to the L TLD.
That's done by Taylor. Did we do that? Right, just Taylor. It's still in that part. It's like LCU. Right. So is it still LCU? Right.
Well, so eventually the whole process will very close to a positive interest specific type. So we deal with error with the whole.
That's something I don't understand. Used to be that when you do the Taylor expansion for Hamiltonian simulation, you know that, I mean, you lose some success probability. And then you use ambiguous amplitude amplification to boost it, because you know you're going to be boosted to 1. It's not permission thing, you don't know the norm. Where are you going to put?
But we don't use amplitude amplification for each LT. We use amplification for
the whole thing. And you keep,
It's a Kraus.
we keep track of the success probability.
I see, I see. Thanks.
And later, I think this was in the spring of last year, we started to think about a different path for constructing algorithms for simulating the Lindblad equation. And we actually, there was an idea in Chunhao's paper that were really intriguing to us. And I think Chunhao also outlined this idea yesterday, which is about approximating this dynamics using the Stinespring form, where the unitary is driven by some dilated Hamiltonian. Okay, and this dilated Hamiltonian looks very simple. So you basically take all your Xiantao operators and position them in the first row and the first column of this new Hamiltonian, and then the system Hamiltonian sits right here. Now, if you plug this unitary operator in here, what it gives you is a first order approximation to the density operator. First order global in terms of the global accuracy, right? And because of these nice sort of operations involved, meaning that over here, you follow a unitary operation, and then after that, you trace out the ancilla. The whole procedure looks very clean, right? You start out with this, and then you apply unitary, you reset the ancilla qubits, and then you just repeat, right? And Chunhao mentioned that this method is only first order, so you have to do this many, many times. So meaning that you have to make the step size very small, and then you have to do many steps of this. So last year we were thinking about whether we can extend this, right? And the advantage of this is that there are many algorithms for simulating this unitary, right? There are many Hamiltonian simulation algorithms for this purpose. So I think last spring, we figured out how to push this to second order, but somehow in the summer, we made it work for any arbitrary order. And this is what I'm going to tell you about in the next few slides. Well, the first thing that we need in order to kind of construct our algorithm is a Kraus form. We could use the same Kraus form that I just told you about, but we came up with another Kraus form approximation that we have a better handle on, right? And this is where I'm kind of bringing back the stochastic differential equation representation of the open quantum system dynamics. Now, that being said, I'm not designing a quantum algorithm to solve this SDE. I'm only using this as a way to construct a Kraus form approximation, okay? And then we are going to map that to a dilated form that's driven by a dilated Hamiltonian. So again, this exactly reproduces the Lindblad equation, right? And so to actually come up with an approximation of arbitrary order, we apply the Ito-Taylor expansion, right? Now this is sort of like the Bible for people who do SDEs, right? So there are a lot of useful formulas there that you can tap into. Now, the reason that this is called the Ito-Taylor form expansion is the following. So if you look at the expansion, the first few terms of the expansion, they look a lot like the Taylor expansion. But then the expansion comes with these integral terms, but these integrals are with respect to the Brownian motion, right? And these are called stochastic integrals. And you don't have to be scared by these stochastic integrals. They are nothing but Gaussian random variables. And they have mean zero, and their variance is completely characterized. And you can look up this book and find all the formulas that you need. Okay. And so once you have this Ito-Taylor expansion, you can plug it into this formula, right? And apply that to the initial quantum state. And what you're getting, you can imagine that there's something that's sandwiched between many of the operators here. And since the covariance of these Gaussian random variables are completely known, you can just plug them in. You don't have to sample them because you only care about the expectation, right? So what this gives you is another Kraus form representation. Okay. Again, we could have started with the formula that we had before, but somehow we have a better handle on these. And two, I think this whole diagram looks very sort of educational in the sense that it gives you like a combination of different interpretation of the Lindblad equation. So this is the unraveling part. And then in the next two slides, I'll show you the Kraus form and the Stinespring form. All right, so it gives you kind of several sort of the integration of these different forms. Now, going from the Kraus form to the Stinespring form is straightforward, right? So the unitary will pick up these Kraus operators in the first column, right? That part is something that we already know. What is non-trivial is to associate this unitary operator to a unitary operator that's driven by a Hamiltonian, okay? And what we found is that you only have to figure out the first column of this Hamiltonian. The submatrix here are all zeros. You can set them to be all zeros. Oh, so well, you don't know the rest of this, and so it's not clear how to simulate this unitary yet.
Of the first row. Okay.
And so in the end, the effort went into figuring out these blocks of this H tilde. And it turns out that we can find all of them to arbitrary order of accuracy. So basically, you solve this, you follow this Hamiltonian dynamics in a bigger space here. And after that, you trace out the additional qubits. And then this becomes an approximation of the Lindblad equation with arbitrary high order of accuracy. So in the next slide, I'm going to give you a high level view of how this is done. And I'm going to share some of my perspectives in terms of getting these different matrix blocks and how they are connected to some of the well-known ideas in numerical methods.
So if I only wanted to order delta t, is it easy to get the Hamiltonian?
And that was the one in the previous slide. So if you just want a first order one, you just go with, sorry, the one that Chunhao had in his paper. This is slightly different from, so his paper actually treated this separately, but it's more or less this Hamiltonian. If this is good for your application, yeah, I think this would be a wonderful method to use. Right, and this is our paper with BN. Here are the steps. So I mentioned before that using the SDE as sort of a starting point and Ito-Taylor expansion, you can derive a Kraus form representation. And the Kraus operators can be expanded in terms of different powers of delta t, right? And because of the sort of a tricky time scale in SDEs, the delta t here can be integer valued and can also be half integer values. So you could start with like delta t to the 1/2, right? And so this is something that you can figure out from the Ito-Taylor expansion. So you can think of these as the input. And then for the blocks in the dilated Hamiltonian that you're looking for, you expand them in a similar form, and you just have to find these coefficients, okay, by matching different powers, okay? And overall, you can follow this diagram, okay? And so you start out with these different leading coefficients, y here, and then from those, you can easily get the leading coefficients in these different blocks. They're actually equal, right? With this determined, you go to the diagonal, right? The leading term in the diagonal block, it depends on these off-diagonal blocks, right? And then with this x00 determined, you can actually move to the next column, and you can determine the coefficients in the next round, and then you repeat. Okay. No, this has nothing to do with that, but it has to do with, I'll mention a few things that might be related, right? So we saw some of these in some other places. So in the theory of ODEs, sometimes we talk about this canonical transformation that map a complicated ODE to simpler ODEs. I'm talking about the normal forms. And over there, you would do something like this, right? Another place that you see something like this is this backward error analysis, right? So if you start with the first order method that I was talking about earlier, and what it gives you is a first order approximation of the Lindblad equation. And then there would be a bunch of correction terms, right? And then what you want to do is you want to make a transformation that annihilates these terms. Then it would become a high order method, right? That's the trick. And so to do that, you need to introduce a near identity transformation and map this H tilde to something else. And that something else, I think, is our H tilde. This part is my speculation. I actually didn't check. It's only my intuition.
Because the BCH is the shadow Hamiltonian for the particular color splitting.
Yeah, that's right. That's true. Yeah, yeah. And the other thing that's nice about this procedure is that it's not limited to time-independent Lindbladians, right? So if you have a Lindblad dynamics where the Hamiltonian or the jump operators depend on time, this method still works. And so in our paper, we actually gave explicit formulas for the first order, second order, and third order methods. Okay, we didn't go to the fourth order because it's like too much.
So you started from Claude and Platon, right? But these weak order schemes are derived for arbitrary observables. While here we are just interested in the quadratic one, right? Because we're just interested in measurement. I'm wondering, have you looked into like whether you can simplify these schemes, the Ito-Taylor schemes, since you just care about quadratic movement?
So I think implicitly we did that because in the Ito-Taylor expansion, some of the stochastic integrals do not have cross correlations. So they are already averaged out. Yeah. But on top of that, I don't know if you can further simplify that. All right, and so in the last few years, there are actually a number of other algorithms. And I'm going to list them here. I'm not going to tell you about exactly what they did. Probably Nathan will talk about his paper on repeated interactions. But there are some sort of, let's say, SDE-based quantum algorithm. For example, the third one, right? There are ideas that's based on vectorization of the Lindblad equation. And we just felt like it doesn't seem to be natural for it to be implemented on quantum circuit, right? And then there are also two recent works about randomized algorithms that were inspired by Q-drift. Well, now that we have some efficient quantum algorithms for simulating Lindblad equation, what can we do with it? So the application that we focused on in the last few years is actually quantum optimal control problems. Okay? The way that you can think about this is the following. So let's say that you either have a closed quantum system where you're simulating the time-dependent Schrödinger equation, or the Lindblad equation, where you, in addition to the terms that you saw in the previous slides, you also have this term that come from external control. For example, you can add dipole terms, and U of t is a control signal. Okay? And you determine the control by minimizing something or maximizing something, depending on the problem that you're interested in. So here, we pose this as a maximization problem. What you do is you maximize the expectation at time capital T, right? Now, the control problem itself doesn't limit the kind of control signals, right? So in order not to have like weird, crazy signals, we put a regularization term right here. Okay? So the way that you can think about this is that for different choices of the external control signal, you end up with different realizations. And you're looking for the one that maximizes this objective function. So that's how we can think about this. Now, unlike closed systems, open quantum systems are, in general, not controllable. So we actually have to treat this as a maximization problem. Okay. So, so it's like whether you can find the appropriate control signals to take the, let's say, the density operator anywhere you want to, right? For closed quantum systems, as long as these dipole operators satisfy some algebraic condition, this is doable, but not for open quantum systems.
Yeah, I think a simple example is just that if you want to control but remain pure, that's, I mean, if your system originally already has some sufficient, but then it's impossible.
It's like when you said O to be like a rank one operator, whether that's true.
Yeah, because you want a pure state in the end, but that's impossible. That's not the case.
But in our paper, so this is a paper that had like 5 authors, and so we actually did a bunch of other things aside from the control problem. We actually tried to sort of like tied up the quantum algorithm for simulating the time-dependent Lindblad. And so we extended this idea of using Duhamel's principle and plus the Kraus form, right, to the time-dependent Lindbladian case. Another thing that we did is to think about interaction pictures. So you could have a Lindblad equation where you have a dominant term, but it looks very simple that can be fast forwarded, right? And we also looked at, this is kind of a trick in Hamiltonian simulation. So this is L1 time scaling. So you have a better complexity in terms of the norm of the Lindbladens, right? So if you want to know the details, you can look at that paper. So that paper turned out not just to be about quantum optimal control, but also about Lindblad simulations. Now, in order to solve this optimization problem, did I go over time? Or, I'm okay. Okay, good. Typically, you have to compute the gradient, right? Especially for large dimensional problems. Now, for quantum systems, it's hard to do backpropagation. So, like it's for quantum algorithms, so it's difficult to go back, right? So, in general, if you were to do this classically, you would run the forward pass and you solve a backward or adjoint problem, and then take some inner product, and that gives you the gradient. But in quantum algorithms, this is very hard to do. And so what we ended up using is this quantum gradient estimation algorithm, which is an improved version of the Jordan's algorithm. Okay? And to apply that, you need to analyze the smoothness of the objective function, and so that's in the paper. And then you also need to discretize the control variable so that it becomes a finite dimensional optimization problem, right? And after that, so using the Lindblad simulation, you end up with a purification of the density operator. And therefore, the objective function that you're trying to compute becomes an expectation. And therefore, you can use these gradient algorithms to compute the derivatives. And to do that, what's involved is a probability oracle that depends on this form, this expectation, to a phase oracle. And then you apply finite difference formula to this. If you apply this repeatedly, but for different x, then you get a finite difference formula, and it's going to approximate the derivative. And then you just use quantum phase estimation, and it's going to recover the gradient. Now, this gradient algorithm is going to produce an approximate gradient with high probability. The complexity of this in this particular setting is linear in time, so it's roughly speaking t over epsilon. We actually didn't use the sort of the optimal complexity that was offered by the algorithm in this paper, partly because their error is measured by the infinity norm. And infinity norms are not straightforward to incorporate in the analysis of the optimization algorithm. So we didn't make the best use of their algorithm. So this could be one of the open problems. So when we consider a hybrid quantum classical algorithm, if the quantum algorithm has an accuracy that's measured by the L infinity norm, can you incorporate it in the analysis of the optimization algorithm? This is one thing that we didn't figure out. So we still felt like there could be a place to improve this dependence. Okay, right, okay. And then, so for the optimization, we just borrowed something. I think at the time when these papers were written, this came from the Berkeley's group. You could do gradient descent, or you could do variants of the gradient descent to get a better complexity. So there are at least two versions that you can combine with. One is the perturbed gradient descent, and the other one is the perturbed accelerated gradient descent. Okay. And this one has a slightly better complexity. So now it's about combining these different pieces together, right? And so the graduate students involved in this project actually spend a lot of time trying to follow these proofs and see whether they can be combined with the quantum algorithms. So this actually took a lot of time to put together. Okay. So overall, if you just want to reach first order stationary point, the complexity is actually very good, compared to some other approaches. But if you want to get to second order stationary point, this is much harder. the epsilon dependence is a lot worse. And so this could be another sort of open problem. So what is the best way in quantum classical algorithms? What's the best way to combine sort of the quantum aspect and the classical optimization algorithms? Okay. So I think this is a good place to summarize and close my talk. So my talk has been mainly focused on quantum algorithms, and I shared our ideas of using the Duhamel's principle together with the Kraus form and then implementing the Kraus form in the quantum algorithm. And the other approach went from the Kraus form to the Stinespring dilation and then determine the shadow Hamiltonian. And there are some extensions to non-Markovian dynamics. And so Chunhao and I wrote a separate paper on that. If you're interested, I can tell you more later on. But one of the open questions here, I think this is also kind of a well-defined problem, is that our previous work actually leveraged a weak coupling assumption so that the error is, let's say, order lambda to the power 3, right? But for strong coupling, how do we simulate a non-Markovian dynamics using quantum algorithms? So I think that's kind of still out there. And for quantum optimal control, we wrote a paper on closed quantum systems and another paper on open quantum systems, which is a lot more complicated. But one thing that's open here is that if you look at the quantum optimal control community, there seems to be a hope for a free lunch, meaning that the energy landscape is actually not that complicated, right? And actually for closed quantum systems, this is more or less known. But for open quantum systems, there are some empirical observations. But how do we translate those nice empirical observations to better optimization complexity? This is, I think, is still an interesting question. So usually to get better optimization complexity, we need to characterize the convexity property of the landscape. But somehow these observations of the control landscape doesn't seem to be directly connected to those convexity assumptions. So with that, those remarks, I'm going to close my talk here, and thank you for your time.
So what are some of the nice properties of the control landscape?
One picture that you will see is that, so here, these are maximization problems, right? So what they observe in some cases is that the maximums are actually along a ridge. So finding one is enough. So, and I think in some cases, there's no saddle point. So you're not going to get stuck there.
But there are also some observations from a variational circuit type of problems where you have this barren plateau.
That's worse. That's bad, right?
Yeah, right. But that can also be seen as a control problem in some sense, right?
That's right. That's true.
So
that's
how
true.
to reconcile these two observations?
So there are definitely some similarities between this and variational quantum algorithm, but for this, it's actually a very structured form. If you look at let's say, controlling a Hamiltonian system, right? So you see this control variable that appears in front of one of the Hamiltonian terms. So it's not like you can arbitrarily choose where those parameters come up. So I think it's probably a subset of the variational quantum algorithms that you cannot initialize at random.
Yeah, I think the quantization is quite important. So it's kind of like in a classical case, if you think about LQR, which is this, then energy landscape is actually not bad. But then if you control, if you do different gates at different times, that's like composites of some variability maps. And then obviously, I think here it's more like this.
in this control, the jump operator is fixed. So what's
Yeah.
the physical motivation for that? You don't control the
So
jump.
we don't control the environment.
Oh, that's the environment.
Yeah,
I see.
yeah.
Is there a analog to the Hamilton-Jacobi-Bellman equation that you eventually want to solve?
Yeah. You can write down those. So the Hamiltonian, right, associated with the variation principle. Right? So all those classical control theory applies here.
What do you mean by Hamiltonian? I mean, it's not the Hamiltonian
So
system.
this is the variational principle behind the control problems. So you can write down this.
Right. Yeah. Mhm. And is that fruitful, or is it just a
For
formal
classical algorithms, it's helpful because actually when you solve the forward and the adjoint problem, you're implicitly solving that problem, the Hamilton-Jacobi-Bellman equation. But for quantum algorithms, we don't have that luxury of solving the adjoint problem.
Right.
Yeah.
Questions? So let's thank Professor Lee again. So I have a 30 minutes break and we'll be coming at 10:30.